So let's get restarted with John Woodruff from Capabilities Limited. John is pushing CHERI performance forward, specializing in capability processor design. He works on microarchitecture, caches, and full system optimization, ensuring CHERI scales without compromising security. So welcome to the stage. I will start this, and you press the right button, I think.
So we've been pushing on CVA6-CHERI implementation, trying to get it ready for people to be able to use. That's okay. My name is Jonathan Woodruff. I'm working on CVA6-CHERI with the team at Capabilities Limited, especially Peter Rugg and Alexandre Genoux, with Simon keeping an eye on us. And we've been improving performance over the last few months in addition to other things, and we did a little study at various points to see how we were doing. So I'm going to talk a little bit about that. All right, so a CVA6-CHERI overview. CVA6, we had previously been working on open source research cores, but now and that was at the university, but now at Capabilities Limited, we're trying to do real work for people to potentially really use. And so we started looking around for open source cores that looked like cores that people might actually put in a chip, which we didn't have a lot of experience doing cores that people put in chips. So we want a starting point that people are using. We looked around, and lots of talk in the RISC-V summits from both companies and also from lots of universities and organizations was around CVA6. So we said, if we're going to have a best chance of having a core that people may be able to actually use in industry, let's try to start with CVA6. And we're happy with that decision, because it turns out it's been a very lively project. It's had lots of improvements since we picked it up, and we've been integrating with those. So when we decided to look at CVA6, we found there was a small consultancy in Portugal called 0 Day Labs that had done a very initial implementation of CHERI for towards a PhD project and research contract with Bruno Sá and his supervisor Sandro Pinto, and they did an initial implementation of the research version of CHERI, so that was useful. We picked that up. We've brought that up to the RV64Y proposed standard, improved area and timing, did lots of verification that Bruno didn't have time to do. We've brought up quite a few bits of software, OpenSBI, CHERI BSD, CHERI Linux, CHERI SEL4, and importantly, rebase. So we brought the code base forward by a couple of years, picking up lots of improvements, including the Superscalar, which we'll see, and also the high-performance data cache, both of which are the main contents of this study. Let's see. I'm sure I pressed the wrong button. Okay, there we go. So as I just mentioned, CVA6 has had quite a bit of work in several generations on making it superscalar, specifically dual issue. Similar to what David Chisnell was mentioning before, there's a real sweet spot for in-order cores where you can issue 2 instructions per cycle. And ARM has a very successful line of processors that does this, and people were pushing CVA6 to that level to be able to do that. And so we moved our CHERI design on top of Superscalar in the way that's made the most sense to us now, and that's working now. We're booting on the FPGA, and we started looking at performance. Then thankfully, there was quite a bit of work in the last few years on a high-performance data cache for CVA6, so a much more parameterizable cache that can handle many transactions at the same time. And this, we were in the previous design of the cache, because it hadn't parameterized certain structures, they were limited to 128, or I should say, 16-byte or 32-byte lines, but they didn't have kind of standard 64-byte lines. And so we definitely wanted that for capabilities because we were making the common work units bigger. But also there's lots of other performance improvements for the high-performance data cache. So we've moved forward to that one now, and we have that working, and we're able to look at performance. Okay, for Superscalar CVA6, this is a publication from the last year. And there was an initial version of Superscalar here where you say they got an average of 29% IPC improvement. And then they did what they're calling CVA6-S+, which allows forwarding from one ALU operation to another ALU operation in the same cycle, where they managed to get the same frequency they were getting with the previous one, or yeah, with the HPDCache they were. And so you can see that the community's been iterating on this design and improving things. I wasn't even that aware of all this history when we just pulled the repo forward and we're like, I guess this is how it works. And so we made everything work. We chose the option of forwarding with an ALU within a cycle. And then when I was throwing together this presentation, I was like, oh, there was a CVA6-S and an S+, and this is the improvements that they were pulling in. But this is the benefit of working with the community. There's somebody working really hard on making this core faster and paying attention to all the details of how the pipeline works, and we just inherit this for our Cherry work. So what did we do? So mostly credit Peter Rugg here. We didn't want to replicate all of the capability logic since it's kind of a floating point logic, and it's not that cheap to put in the pipeline. We could have replicated it, but we only put it on one of the ALUs. It specifically consumes the output of ALU 0 and of the branch unit because there are some capability operations that are branches, and this is more or less where our capability logic unit was before, so we just kept it on that one. And the downside of this arrangement is that we can't schedule a branch and another capability logic operation in the same cycle. But otherwise, we're flexible with loads, stores, floating point, which probably doesn't happen that often, and multiply. We can schedule alongside a capability operation. So we'll see how that goes in the next slide. So this is a graph of the IPC for legacy and PureCap, and you can see when we don't have Superscalar on the green one and the blue one, we have a pretty similar IPC across all of these MyBench benchmarks and also a couple of Olden benchmarks. But when we go to two-way, there's a big jump in instructions per clock performance. And the PureCap one at the minute doesn't quite increase as much as the non-capability code. Now, this is likely due to our scheduling restrictions. So we're going to keep playing with this, see if we can get the same improvement with capability code as we have with non-capability. There may be an option in there so we could save area, or maybe we'll just spend all the area and get maximum performance. But hopefully we'll keep pushing on that. But it's nice that we've inherited a big performance jump here for dual issue. Now, the high-performance data cache is the next one, and there's another whole stream of publications on this high-performance data cache for CVA6, where particularly with these memory-based benchmarks, they have very large performance improvements for this data cache. So, for example, you can run 8 load instructions in a row, and when in my visualization of a classic in-order pipeline, you'd get stuck on the first maybe couple loads and wait for them to come back. But CVA6 is able to get all 8 loads to the end of the pipeline, get them all out to memory, and have them come back, which is nice to have when you're doing these kind of memory streaming benchmarks. You can overlap the latency, and the high-performance data cache is able to do that. So we wanted that. Now, there was a challenge with the high-performance data cache because we needed to tag updates in there in a way they didn't before. So we had to switch between 2 different designs of that to get it efficient. We also, the high-performance data cache is extremely parameterizable, but one parameter they hadn't considered yet is that your read word width into the core would be wider than your backing data connection to the data bus. So we had to make things more flexible in several places to make that work. Anyway, we've managed to do it. Alexander Genou did a lot of the work on that one. And of course, we were excited about being able to use 64-byte cache lines which make a big difference for us as well. So now here's the performance on SPEC benchmarks running in FPGA, which we managed to get going just last week, or yeah, I think it was pretty much last week or the week before. And you can see with dual issue, we had a good performance improvement, and with dual issue plus the HPDCache, on average, we're eliminating 31% of the cycles from the runs of these benchmarks. So it's a big jump there. It looks like memory has a much bigger improvement than you might expect, but these SPEC benchmarks are really big. They push the memory pipeline, so most of our improvement is coming from the HPDCache, but dual issue has a big effect as well. And the HPDCache also manages to eliminate more than half of the data cache load misses, likely due to the larger cache line size, but also it's a write back configuration rather than write through. The old one was quite simple, so it was write through. So that's really good. I guess we have a couple minutes for questions if anyone wants an update.
Okay, we have a question at the back. Yeah.
Any idea what was going on with Patricia?
So let me go back. So on this one?
Yeah.
Oh, that it just has a low. So Patricia is, I don't know why it has a low IPC in general. You're saying why didn't it benefit from dual
It looks
issue?
like it does better with PureCap than legacy.
Well, this is IPC. So this is IPC. So we're not actually seeing in a way it's not, so it's different code. And so in some PureCap benchmarks, they have some code growth. So there may be extra instructions to do certain operations. And often the extra instructions that you get in PureCap mode are arithmetic instructions. So they may schedule a bit better, and then you get a higher IPC. That doesn't mean the performance is actually better. It means the pipeline's able to chew through more instructions, which it may need to do. So I'd need to look and see what the performance is with Patricia. But Patricia is quite pointer heavy, and it's doing a lot of graph operations. So it's quite possible that the code just diverges more in that one than in most of them.
Sorry, it's just something that jumped out.
It also doesn't have a very big jump for two-way in general, which might be due to having quite a few memory operations that aren't necessarily schedulable in the same cycle.
Okay, it's a bit dangerous. Okay, no further questions. Okay, so thank you very much, John.